speaker, yeah.
Yeah, I think this brings us to the second part of the workshop. We're going to jump right in. Just a quick reminder to everyone, if you joined in just for the second session, that we'll be taking all our questions through Slido, which is available on our website under the Q&A tab. We'll also be sharing links during the talk. Let's jump right into the second half of the workshop. And what better way to do that than by welcoming Professor Nora Ayanian from the University of Southern California, where she works on solutions for end-to-end multi-robot coordination. So Nora, you should already have the privileges, and you can screen share and take it away. Just so you know, the talks are 20 minutes and then 5 minutes of Q&A.
Yes. Okay. Everyone can see my slides?
Yes.
Slide. Okay, great. I guess I missed the email about giving my talk title. So my talk title was TBA, which was fine because I came up with something different anyway. I'm going to talk today about diversity enhanced autonomy for robot teams. This is actually more like a blue sky talk as opposed to things that have been done. So I'll spend a little bit more time kind of motivating, why I think we need diversity enhanced autonomy. And then I will kind of tell you what we've done along those lines. So first, let me start by, obviously this is a multi-robot workshop. And, there's a lot of multi-robot systems that are in the real world, not in unstructured environments and stuff, but, so here's an example. I know this is a single robot, so this is actually Happy. I own this robot, and Happy is great. It cleans my floors and does a pretty decent job as long as I clean up for it in advance. And so I thought, iRobot has what they call their dream team, which is both the vacuum and the mop, which they kind of present like a multi-robot team. But, they're great on their own, Happy and Moppy. We call this one Moppy. But calling them a team is really a stretch. So let's just say that Happy and Moppy used to live in the same room, but now they don't anymore. They really don't play well together. So why? This is because having multiple robots in one space is a hard problem. And you don't have to be a roboticist to understand this. Anyone who's observed children, multiple children, or even sometimes adults together would know that the difficulty isn't in the individuals. So there's nothing wrong with just Happy or just Moppy. It's in the interaction. So what happens when they're sharing space, they're sharing resources? Robots sharing, though, can do really amazing things, right? So look at what they've done in manufacturing, in warehousing, and arguably even the self-driving car. We've made a lot of, we've had a lot of successful efforts. So why do we still care about multi-robot systems? Well, while robot sharing can do amazing things, if we forget the fact that they're sharing, so teams of robots can also fail miserably, right? So if we ignore that they're sharing space, this kind of thing can happen. So this is when we first started flying the Crazy Swarm. And we kind of forgot about the interaction between the robots, the downwash, and this kind of led to some of our work on downwash aware multi-robot planning. But basically you can see like the ground effects here, and just generally the airflow, the downwash really affected everything. And then we have this kind of impossible explosion. So modeling this kind of interaction can be really difficult or even impossible. But we shouldn't avoid things that are hard to model because this totally limits the potential of multi-robot systems. And so in case you didn't see that video, because maybe it's short and you maybe blink, so let me show you again. So the robots take off, it looks great. And then for a second, I think, wow, this is really cool. And then, oh, wait, never mind. And they all fall on the concrete floor. So I'm interested in multi-robot systems because of their potential to solve really difficult problems of great impact, such as responding to wildfires, searching for survivors after an earthquake, or even extraplanetary exploration. So our existing solutions don't work here because there are factors at play that are really hard to model. And our existing solutions, which make many assumptions to compensate for modeling difficulty or tractability, will just not work. But by overcoming these challenges, the impact that we can have is huge. So take just the first example of responding to wildfires. So in 2020, in California alone, more than 4 million acres burned in wildfires. 4 million. The August Complex Fire, which was the first ever gigafire, burned more than 1 million acres. I mean, let that sink in. 1 million acres for one wildfire. More than 10,000 structures were damaged, and there were 33 deaths. So this is a huge amount of impact that we can have. So generally, when you think of responding to wildfires, this is the image that comes to mind. So planes dropping fire retardant or planes dropping water. And in fact, I actually saw this from my own backyard last year, which is a little bit scary to see, planes flying in the hills and dropping fire retardant. It's very scary. So while there's an urge to throw everything that we can at a wildfire to stop it, the conventional wisdom is that aerial firefighting only works in the initial attack. So when the fire has just begun, to keep it from spreading and to kind of buy time for firefighters to get there. Once that initial window of effectiveness is gone, it's not helpful, really. I mean, imagine trying to fight a million acre fire with a handful of airplanes. So we need to be really fast. And then pilots put their lives in danger by flying less than 200 feet above the ground with very limited visibility. Wildfires also make their own weather, so there's so much unpredictability. So the urgency with which we need to do this, as well as the danger, makes it a perfect candidate for a team of autonomous aerial vehicles, right? Because we have to do it fast. But right now, we don't really have the technology to do that. So let's go back to these examples and let's talk about what makes them different than manufacturing, warehousing, and autonomous driving. So our solution criteria is similar. We want full autonomy and we want automatic control synthesis. So we don't want to have to hand control the airplanes. We don't want to have to, have somebody come and tune all of our parameters perfectly so that it works for this wildfire or that wildfire. On top of that, we want guaranteed performance. And there's obviously constraints and safety concerns that we have to take into account. But these scenarios present us with very different challenges. So first, there's very little structure to exploit, like there is in manufacturing, warehousing, or driving on roads. On top of that, there's dynamics. The robots are dynamical systems. We can't perfectly model them. There's dynamics coming from the environment. There's uncertainty in the environment. And from that of the robots themselves to those of things that are actually moving in the environment, the interactions between the robot and the environment. And then, of course, we have the curse of dimensionality and combinatorics. So the problem grows exponentially in the number of robots and the number of time steps. So these are significant challenges that are not currently addressed in multi-robot systems. And part of the reason is that the way that we solve problems is to make a bunch of assumptions to make it tractable. So some of the assumptions we might make are that our system is holonomic, that we have unbounded acceleration, that we solve the problem in discrete space and we can just apply it to continuous space, that we have unlimited energy. So the trouble is that this then leads to brittle solutions that don't work in dynamic, cluttered, uncertain, or unstructured environments. And so we need to kind of take a toolbox approach and kind of take different fields and kind of combine them into robotics and try to figure out, how we can really leverage advances in other fields so that we can make advances in robotics, specifically to getting multi-robot systems into the real world. So my work kind of pulls on a bunch of different, so this is my toolbox, it pulls on a bunch of different fields like learning, AI, control, games, vision, and social behavior. So obviously I can't tell you everything today. So I'm just actually going to talk about what we're trying to learn from social behavior in diversity enhanced autonomy. So, humans are really good at navigating things, right? So, if I had a team of robots try to navigate this intersection in a totally independent way, I think I would have a complete failure. But humans manage to do it okay, right? Obviously, there might be some, shoulders brushed or people bumping into each other, but that's generally okay, right? Obviously, we don't want our quadcopters to do that, but it's okay for them to come a little bit close to each other. But humans are really good at doing this. So why can't we do this for our teams of robots? So what I believe the problem is that generally, in order to solve a multi-robot problem, we say, okay, this is the problem that I want to solve. And then that problem, for example, is containing a wildfire, right? So then I say, okay, well, I'm going to make assumptions about how the fire is going to grow and what the dryness of the vegetation is and which way the wind is going to blow. And, basically a lot of different assumptions, right? And then what happens is once my assumptions are made, I take them and I maybe come up with what I think is the optimal solution. So it's the optimal solution for the problem defined with those assumptions. The trouble is that when my assumptions are not met, that my solution breaks. And because I've deployed the solution on every one of my robots, right? I came up with the optimal controller, so why shouldn't I put it on all of my robots? Then what happens is they all fail and I have nothing. And so my belief is that what we should instead do is come up with our problem and then maybe think about what different assumptions could be. Well, maybe if the wind speed is this, or if the wind speed is that, and then we come up with different solutions that correspond to each of those assumptions. Because we can't obviously solve the problem with every possible capability. But if we can narrow down certain likelihoods, maybe not just to one set of assumptions, but to several sets of assumptions, and then we can deploy all of those solutions, or maybe the best of those solutions on our team of robots, so that each robot makes different types of decisions, then what we can do is we can have diversity in our team of robots. And then with that diversity, we'll be able to solve more difficult, more challenging problems where we can't possibly know everything about everything. And so if I deploy this on my team of robots, then maybe what I can do is I can have my robots doing different things, and then they can observe and learn from each other. They can learn from their own failures and their neighbors' failures, and their own successes and their neighbors' successes. And of course, science has shown that diversity in knowledge leads to higher quality solutions. So I'm sure all of you have worked in groups before. And when you work in a group, you don't really want 10 copies of yourself, because that's not very helpful. If you work in a group on a difficult problem, you want people with different capabilities and different backgrounds, different experiences. And so why aren't we doing this for teams of robots? So what I propose that we do is to really kind of take a hard look at how we treat our teams of robots and think about how we can incorporate diversity in our solutions, not just physical diversity, so not just heterogeneous teams of robots in the sense of their physical presence, but heterogeneity in their controllers, and then combining kind of learning with that so that we can now learn from each other and learn from our mistakes and adjust as we go. I believe that this is really the only way that will actually get teams of robots in the real world, and not solving just arbitrarily small, lab-defined problems, but real difficult problems. So in order to really study this, what we did is we decided that we wanted to see if robots could act like humans. So can robots navigate this, this intersection? And so, because humans are very good at that kind of coordination. But obviously, robots and humans are not the same, right? So robots and humans communicate differently, right? So just by looking at this child's face, you can see she's happy, she's communicating something. But robots, just by looking at each other, generally can't communicate anything. And so robots, beyond communication and expression, right? Robots have constraints on communication, motion, sensing, processing. So basically, robots are not humans. Obviously, we know that. But robots also have a very different perspective on the environment. So here's a video of what the world looks like from a robot's perspective. So here we have iRobot creates, one of them has a camera on board, and they're actually trying to form a circle. So these are actually my students remote controlling the robots. But imagine if the robot only sees this view, how would they even know how to form a circle? Right now, it kind of looks like maybe the robots have formed a circle, but if you're asking the robots to do a task, you have to keep in mind their capabilities and what their perceptive systems are. So obviously, robots have different constraints on communication, motion, sensing, and processing, and robots are not humans, right? So humans can communicate by pointing at things. Robots can't point at things, right? They can't do a lot of things that humans can do. So it's really difficult to try to say, okay, let's try to learn directly from humans. So what we decided to do instead is to see if humans can coordinate under robot-like conditions. Now we want robots to do these really difficult tasks under these imposed restrictions that we put on them. Like, you can't have this much communication. You have to maintain, a certain amount of energy. You have this kind of, perceptive system. So if we gave humans these tasks and put them in a robot-like environment, would humans actually be able to solve it? Because if they can't, then we're asking robots to do too much. So we asked the question, can humans coordinate under robot-like conditions? And to do that, to answer that question, what we did was we built a multiplayer game. And in this multiplayer game, if you were playing the game, this is you, but there's other people playing the game with you. And so you can see all these other dots around here. So these are all other players playing the game. And everyone's playing on their own screen, but they don't get to see this view. What they see is this. So this is what robots would see. So this is what a human would see. So imagine that the robot has a sonar or a LiDAR. And so they see kind of the closest object around them for some limited distance. And, what we did is we said, okay, now what we want to do is we want to have these human players form shapes like circles and rectangles, something arbitrary, something easy, so that, and only with this limited view. So what they can do is they can move up, down, left, or right. And that's basically it. There's no explicit communication built into the game. So there's no messaging others, because it was really difficult to figure out how to kind of convert robot-like communication into a screen. And then there's this shared playing field, which they don't actually see while playing the game. And on the shared playing field, we want them to form a circle or a rectangle. So this is what it looks like when you're actually playing the game. So this is you, the red dot, you can move around. The reason that the environment is tiled is so that if you're alone by yourself, you actually know that you're moving. That's really the only reason that it's tiled. And so as this person moves around the screen, you can kind of see all the other agents that are playing the game. And this is a small group, but so it's easy to kind of see what's going on. But when you have a large group, like for example, this one, it's a little bit more difficult. So in this game, we ask the players to form a rectangle. And what will happen in the beginning, and it happens pretty quickly, is that they start forming kind of rectangles in different places, and eventually they come together. So again, they have a limited field of view. So like this guy can only see this much around. So multiple rectangles start forming. Eventually they get to 2. And then some players realize by kind of moving around that there aren't enough players here. So they go out to look for others. And this guy goes and finds the other group. And then he goes back to actually recruit the others. And then they all kind of come back differently. Some of them even start forming rectangles in arbitrary places. I don't really understand, but everybody plays the game differently. And so this guy kind of does a lawnmower motion to try to find their way back to the group. And eventually they form something like a rectangle. What happens in the end is that they form something very close to a rectangle. And you can see that they're actually communicating with each other. So while we don't have explicit communication in the game, by bumping into each other, they're communicating and saying like, hey, you have to move. You're not in the right spot. You move away, move out, follow me. These kinds of things are all being communicated through motion. And what happens is some players haven't really moved at all for the entire game. And they're just fine with that. And then there are players that go out and recruit others. So everybody plays the game very differently. And I think this is what makes it work. If everybody was equally stubborn, then we would have pieces of rectangles everywhere and nobody would ever converge. So we have that game, and what we're trying to do is we're trying to learn the decision policies that players use and actually implement them on real robots. So this is something that we have ongoing right now. Some other things that we're planning on doing with this information or with this game is to provide an even more realistic robot perspective. So obviously not, robots generally can see in front of them and not an entire 360 view. Sometimes they can. We want to try to isolate challenging scenarios one player at a time. This is because it's really difficult to really analyze what people are doing when everything is moving at once. And then what I think is really key that we can do with this is we can introduce obstacles in the space. I think it would still work and humans would still actually be able to do this. Actually, when humans did this the first time, I was very shocked. I really didn't think that they would be able to. So I was pleasantly shocked that it actually worked. And so now we think, okay, let's make this more difficult by introducing uncertainty in the environment, introducing dynamics. And then another thing that we can do is really to alter the agent response to human input. So when you press up, maybe it moves more slowly than when you press down, so that it's kind of like the agent is moving on different terrain. And what is it that we actually want to learn from here? So how critical is diversity? I would argue that it's extremely important. If everybody played the game the same way, like I mentioned, then I don't think it would have worked at all. Beyond that, how can we quantify diversity? Can we put a number on it? Can we give some meaningful value that will help us to build better teams? What are the ideal combinations of player types? If once we figure out what the player types are, how many of the assertive type do we need? How many of the passive type do we need in order to make this work better? Another thing that we want to learn is how do players cope with dynamic or unknown environments? And finally, how can we build more effective teams? And this is actually relevant not only in robotics, but beyond robotics, right? So like, how do we build more effective people teams? And so what I propose that we do is that we take this kind of diversity approach. And I think that this will help us address some of these assumptions that we make. So maybe not all of them at once, but certainly, perfect execution, synchronizations, assuming that the world and the tasks are static, that we have accurate maps, and so on. So I think that really this can really help us try to achieve real robots in the real world. And so in conclusion, if we learn to leverage diversity, we can rely on fewer simplifying assumptions so that we can deploy robot swarms in the real world. So this work was actually sponsored by the National Science Foundation and the Akawa Foundation, and it included work done by my graduate students, Wolfgang Honig, who's responsible for the Crazy Swarm, and the game part was done by my student, Libby Borosin. Okay, that's all I have.
Thank you very much, Nora. Thanks for finishing right on time as well. That was super interesting. I think I would have been the person not moving at all or going off into a corner. It was actually impressive. Let's see. I will check on Slido. So we have a question on Slido. So teams with diverse strategies may better achieve resilience. How could we test and evaluate for this kind of resilience, like testing against unknown unknowns?
That's a really good question. I'm not sure I have a good answer to that. I think just, throwing things at it that we can, obviously, testing it in the lab is not going to be enough, but really just testing it under real world environments. I think that's kind of the best way. And then you just hope. I don't think that, I don't think that we'll be relying on, drones to fight fires when they're not quite ready yet, for example. I think that we can kind of test them out in these scenarios before we're actually relying on them. And I think that's probably just the best way to do it. There's always going to be unknown unknowns. And I'm not sure that we can really test for all of them.
Yeah. All right, let's see. We're seeing more questions pop up. Maybe one more. We have time for one more. If humans can achieve tasks as if they were robots, didn't we just learn that we need more computational power? How do we sort of inform robot and algorithm design from this kind of an experiment?
I don't think that it means that we need more computational power. I think it means we need to think more creatively. And I think that it really just means that we need to be able to leverage diversity. I really don't think it has anything to do with computational power.
Right. Something that was interesting also was that I was wondering this as I was seeing the picture of how the players were moving around, is that diversity could have actually evolved also, right, during that experiment. So
yes.
People could have decided to behave differently on the fly.
Yeah. So actually, when we played the game, well, the way that we did it was we had players play like 7 different takes of the game. And then each time we actually started with the players very close together and then kind of spread them out in the space over time. And even though we did that, they got much better at playing the game and they solved it much faster. So the further we went on, the better they did it. And so they became a better team over time with practice. But in general, players took the same role through all of it. So if they were pretty passive in the first one, they were pretty passive in the last one. And if they were, if they took leadership in the first one, they took leadership in the last one. So the way they did it probably changed, but their roles didn't change too much.
Okay. So it's like a local change. Okay. All right. I think we should move on to our next talk. So thank you so much, Nora. There are some more questions popping up on Slido. So if you have some time, maybe you could go on the website and answer some questions there. If not, no worries. We can also get to them at the panel. Yeah.
Sure.
Okay, awesome.